Welcome everyone to another edition of the Finite Element Seminar at Lawrence Livermore National Lab. It's a great privilege today to have Professor Stefan Turek from TU Dortmund here. So he's been at Dortmund for more than 20 years, has a big research group. I think he's still the department head. Done a lot of work in incompressible flow, finite elements, flux-corrected transport, all sorts of things that we're interested in. And today he's going to talk about algorithms that are parallel and target low precision accelerator hardware, also something very, very interesting for us. Stefan, thank you so much for agreeing to come and from calling us from Europe. The floor is yours.
Yeah, thank you very much for this invitation. So as I said before, it's my second visit in Lawrence Livermore. The last was in 1992 in presence at that time meeting Phil Gresham. So I decided I want to talk about what we call hardware-oriented numerics. So it's a special field inside of numerics for PDEs. And I want to talk about our techniques or what we want to do for hardware-oriented numerics for massively parallel and low precision accelerator hardware. So mainly it will be NVIDIA. And it's clear, since I'm a CFD guy, I will talk about application to large scale CFD problems. And the subtitle is simply faster and more reliable predictions are needed. So let me start with the motivation. And now I have the first problem. Okay, now it works. So the motivation is, at least for me, and perhaps you're in the same situation, since last year, I get more and more articles like that. So, and in the focus, there's mainly artificial intelligence. Then you find such an article which says artificial intelligence is able to make weather prediction. Okay, why not? You read conventional weather forecasting is based on mathematical models. That's clear. So it's the Navier-Stokes equations. Then you can read it's very fast. It's by orders of magnitude cheaper than conventional simulation models. Okay, perhaps. And you also have to read the quality is of similar type like what we do with Navier-Stokes. I doubt about. And then you also have to read in future, it will be much better. And in principle, AI will be able to do simulation predictions in minutes where we might take months or years. And that, at least I myself cannot believe. So I'm doing CFD since more than 30 years. And I think what we do is not so bad, but yeah, so to see such announcement, I'm very skeptic. On the other hand, it's clear. So I see for us, and with us, I mean the mathematical fluid mechanics community and the CFD communities. In some sense, we have to change our style of working, or we have to work harder, because I feel a little bit that we might be displaced by artificial intelligence. And with displaced, I mean, I see it already in Germany. So if you want to get funding, it's getting harder and harder for CFD based on finite element simulations and similar. So much more sexy are projects with AI, machine learning, and so on. There are also rumors that perhaps the money for universities, for math departments will get reduced because math is getting less and less important. Do everything with AI. We had the initiative in Germany, 1,000 new professors in AI. Fine, but there was not only one professor in mathematics at the same time. So I think this can be a bad situation for us as mathematicians. And on the other hand, it's also bad for AI, because I think what is very necessary if AI and CFD work together. So we should be able to generate accurate training data, and without accurate training data, I would say AI has no chance at all. So that means my vision since many years and also for the next years is I believe that we in the mathematical CFD community, on one hand, we should be able to provide much more accurate simulation results, because I think that is the problem of AI, the accuracy. In principle, we know the approaches since more than 30 years. So buzzwords like user-specific, goal-oriented a posteriori error control, the mechanisms are clear, but I have to confess, I do not know any production code in CFD which ever realized such things. So theoretical, perhaps we might have a feeling, how can it work? But in real life, I do not see. And my personal experience is, the problem is, this a posteriori error control, in many cases at the moment, it takes 10 times or perhaps 100 times more numerical effort. And the problem is, if I want to apply it for a fully non-stationary 3D simulation, which perhaps takes 1 day, it doesn't make sense, because you might get a very good, reliable result where you may trust it, but if it takes 100 days, it doesn't make sense. So it means before I think we really might get successful with a posteriori error control, first of all, the simulation tools must get much more efficient. And that I mean more efficient with respect to numerical, computational, and also algorithmic improvements. And at the same time, we must be able to exploit much better this huge supercomputing power. So it means here in this talk, I will mainly concentrate on the aspects of efficiency, how to speed up CFD solvers by, I hope, several orders of magnitude. But it's clear in the background, I think accuracy might be much more important, especially with respect to AI, but that, at least for me, will be the next step. So what does it mean to be more efficient? So I just checked and I figured out Lawrence Livermore seems to be the _1 in the world. So there is this new _1 in the top 500. It's El Capitan. So 11 million cores, 1.7 exaflop. And I want to compare it with the _1 in 1996. So I will explain you later why 1996. But if you compare, at that time, it was a Hitachi machine, 220 gigaflop. So that means now, 28 years later, the computational power is more than 1 million stronger. In fact, it's 8 million. But let's say for the next steps, today we are 1 million times faster than 1996. In principle, I don't know, so you know it better. Sometimes I follow Elon Musk, but more not Elon Musk, but his Colossus project, which in my opinion, a very interesting computer. So when I tried to calculate, it looked like 3.4 exaflop and even almost 50 exaflop in tensor core, single float, single precision, very interesting machine. And it also shows me, beside the top 500, there seem to be much more computers, perhaps much faster computers. And I'm just interested, how could we in future exploit such computers? So it's not only the _1. So if you just compare the average and so on, you really can say, compared to 1961, so the compute power has increased by a factor of more than 1 million. So why 1996? In fact, oh, I really feel old, but in 1996, I was involved in one of the, what I call successful benchmark initiatives. There was the flow around cylinder benchmark series. In fact, that was part of German fundings. It was in 1996. In 2006, this was extended. Perhaps some of you know the fluid structure interaction benchmark. And then it was also extended towards a multi-phase benchmark, rising bubble. So these are 3 initiatives I was involved. It started in 1996. And I see it's really getting more and more important. So on one hand, it seems to be, or they seem to be well accepted tools. And you need them if you want to evaluate what is the realistic quality of learning, or for me, unconventional tools like Lattice Boltzmann, SPH, and so on. So they're coming, they claim we are much better than finite elements and so on. And then I think you need a tool how to analyze, with which you can analyze how good is it really. So it is it seems to be well accepted because I did this last September. I figured out my top one journal is this old benchmark paper. So it was cited more than 1,000 times. My number 4 paper is this FSI paper, and my number 6 is this rising bubble. So it shows me even today, there is a need for such kind of benchmarking tools in a quantitative way. So these benchmarks are quite easy. So there's a 2D and a 3D version. It's flow around a cylinder or flow around a square. There's a steady variant, bench 1. There's a Van Karman vortex shedding variant, bench 2. And there is a bench 3, where you have to calculate for exactly 8 seconds, and the inflow speed is going up, going down. And now, in 1996, I did it on an IBM SP2, at that time with 6 million unknowns. And it means, keeping in mind that today I should have more than 1 million times more compute power. In principle, I should be able to do the same simulations in one day with at least 10 trillion unknowns. I have to confess, I cannot do that. We just repeated some of the calculations last year with, let's say, more than 1 billion unknowns. And just to show you how good we are today. So, and I talk about Reynolds 20. This is stationary. So some of you might say it's a toy problem, Reynolds 20. For 2D flow around cylinder, we know the reference results up to 10 digits. 2D flow around a square, much harder, so you have less regularity and without special adaptivity scheme. So this is a uniform refinement with a pre-adapted mesh. So you might get 5 digits. To do the same in 3D for the flow around cylinder, it's also nice to have 5 or 6 digits. What surprised me, flow a 3D Reynolds 20 flow around the square, we are not even sure about the 3rd digit. And at the moment, we extended to do another level of grid refinement. We are in the range of 10 billion unknowns. But even then, I'm not able to predict the drag and lift for this simple Reynolds 20 flow around the square. And that means we are in 2025. And so at least I'm unable, with all the compute power and algorithmic power I have, perhaps someone else can do that, or you should try it. But this is really an open problem at the moment. Prediction of these values with higher accuracy in 2025. So it means one thing is clear. So the compute power increased in the last more than 20 years by more than factor 1 million. But it seems at least our techniques did not scale in the same way. And so it's clear there's something what we do in a wrong way. And so the question is, how could we do it much better to get much more efficient CFD simulation tools? So that means to do this, and since I call it hardware-oriented numerics is always a little bit looking what kind of hardware is available, and then to adapt the numerics. And then if I just check the top 500 from the last November, and you see 2 trends. The one is massive parallelism. So all computers in the top 10 have more than 1 million cores, and all of them have special accelerators, in most cases NVIDIA or AMD. And I think for me, the available HPC compute power is just the number of cores times the teraflop per core, or the number of nodes times the teraflop per node. So this is what I have in mind if I talk about extreme HPC compute power. So I do not want to talk about the number 1 because El Capitan, this is too new for me. So this is something what I did last year in October. I just checked a little bit Frontier. Frontier was last June the number 1 in the world, 1.2 exaflop. Then I was trying to figure out how much of this compute power, so more than 1 exaflop, is due to CPUs and how much is due to the GPUs. It was very frustrating for me. In principle, the GPUs are delivering almost 99%, and this AMD EPICs are giving only 19 petaflop. So, and this is the result if you do not exploit the matrix cores or the tensor cores for NVIDIA. If you add the matrix cores, so for AMD, it increases in double precision the speed by a factor of 2, then potentially, in my opinion, Frontier might be a 3.6 exaflop machine, but to get 1.2, I think is very fine. But much more interesting is if you see these pink plots, because that shows NVIDIA, and in my opinion, NVIDIA has really invested a lot in lower precision. So I also have to confess, still today, I was not able to get access to this AMD accelerator hardware. I'm familiar with NVIDIA. And NVIDIA is for me very interesting because there is this huge gap between double precision and single precision. So you see here, if we talk about even the H100, which is quite old already, so we talk about 500 teraflop in single precision if you exploit also the tensor cores. And that is, I'm interested, how could I exploit it in future? So that means, for me, the main question for the next minutes is, so how could we exploit massively parallel hardware and also lower precision accelerator hardware? And what I want to show you as components for this, something what we call prehandling. So it's important to exploit lower precision. And I will talk about global in time, respectively parallel in time or simultaneous in time multigrid solvers, which we design really to exploit parallelism also in time. So, and to do this for large scale CFD problems. What do you mean by large scale CFD? So here you see the Navier-Stokes equation. And okay, if you want to handle it, you need Austen type solvers, so linearized Navier-Stokes. You have Poisson problems. You have to solve convection diffusion problems. And I think in the last 20, 30, 40 years, we have developed a lot of very excellent tools for this. The problem is, if you talk about large scale or on an industrial scale, you have also complex geometries. What you see here is a typical twin screw simulation, so with a very dynamic behavior. But at the moment, I want to talk about what we do. It's called, these are extrusion dies who do not have access to large compute facilities, typically can work everything via internet, via World Wide Web. So there is a tool for a parametric generation of digital twins. So you more or less describe the CAD file, the CAD description. Then our part is based on the surface generation. We make a full automatic 3D mesh generation. Then everything is transferred to a supercomputer to make the simulation. And the company at the end gets a kind of automatic reporting of the results and recommendation. So it means our part is step 2 and step 3. For instance, here you see the CAD description, and then we design corresponding course measures, which then during multigrid will get refined. So it looks a little bit like that, what you see here, almost in real time, how we construct corresponding 3D course meshes for such a device. And what I talk about here, this is the course mesh. So, and a typical application looks like that. You see on the left side the machine, and the aim is you press the polymer through this apparatus, and then at the end, through the given holes and the outlet, you want to have an outflow which is more or less very homogeneous, everywhere of the same size. And so the question is that, as you may imagine, doesn't happen in real life. So you have to modify this machine inside. So, and whatever you do is take care that between inflow and outflow, you do something so that the outflow is homogeneous. The problem is you cannot take a look what's going inside. So you have to do it by numerical simulation. What you see on the right side is a corresponding typical course mesh. And here you see already a problem. The course mesh already consists of 68,000 elements, hexaedral elements, and the course grid problem is 2 million, which is already quite high, 2 million. Typically, we work at the moment on level 4. These are 930 million degrees of freedom, but from the point of accuracy, I would say level 5 is important, might be the right one. So we talk about 8 billion unknowns for one simulation. And that's only one simulation because you have to plug this into an optimizer, because at the end, you want to get the optimal device. An alternative, we work at the moment, let's say, with more octree-based techniques, that we say the coarse mesh is much coarser. So we do not refine the mesh already in a coarse mesh, but then during refinement, you come closer and closer to the final geometry. And so it's clear this might take much more unknowns, but on the other hand, it might be better for GPUs and similar things because the data structures are much more easy. And then a typical simulation looks like that. You see different stages. Prototype 1 is the first candidate. Prototype 4 is the final result. And what you should see, you see on the left side such kind of fingers. And these fingers you do not want to have, because that means this is the outflow profile, and there are zones where the outflow is much too fast. While on the right side, it's more homogeneous. And that is the result for such a domain or configuration after 4 optimization steps. And in each optimization step, you have to solve such corresponding problems with, let's say, 8 billion unknowns, fully nonlinear. It's a complex material. And there's automatic remeshing because you adapt the geometry inside of the device at the end then to produce this homogeneous outflow. Okay, so this is a typical problem, what we do together with this company for mid-range, let's say, industrial companies in Germany and Europe. And as I said, we want to exploit, or we have it running on big machines. And my motivation was, if we want to exploit the typical HPC facilities, so it means millions of cores, accelerators. So first problem, let's say you have a machine with 10 million cores. Then it's clear you want to parallelize it. But the problem is, so very often in space, the problems are not large enough. So even if you have 100 million unknowns in space, that's nothing for 10 million cores. And typically you see here what happens if you solve, let's say, the heat equation with a standard solver, and you want to add more and more CPUs, and you do the parallelization only in space. Then after some time, you see adding more and more CPUs doesn't help. So if you switch to what we call parallel or simultaneous in time, that means we make the problem bigger by treating here, for instance, 1,000 time steps simultaneously, and we want to preserve that the numerical properties of the solvers are similar, then we have much better chances to get better scaling effects. So it means you see here, treating 1,000 time steps simultaneously, we can even handle with 1,000 cores, and the scaling is still quite fine. The next step is all these accelerators. So as I said, so far I was unable to get access to this AMD boards. I also so far have not access to Trainium 2 by Amazon, which is for me also quite interesting hardware. I'm more familiar with NVIDIA. And here you see what happens switching from the Volta to the Ampere A100, then the Hopper, and now we have the Blackwell. Surprisingly, for Blackwell, it even happens the double precision did not improve at all. This is the B200. I think the B100 has in fact only 30 teraflop, so which is even slower than the H100. Tensor Core doesn't help much, but if you switch to lower precision, especially this Tensor Core TF32, you see an enormous speed up. So we talk about 2,200 teraflop, and yes, that is a huge number I want to exploit. Trainium, I don't know whether one of you has experience with this Amazon machines. So I didn't find anything about double precision, but it seems if you would be able to work in single precision, this is a quite interesting hardware. So we talk about in TF32, so Tensor Core, floating point, single precision, more than 600 teraflop. But what is clear, so if you check this accelerator hardware, we talk about theoretically available peak rates in the range of several hundreds of teraflop. The question is, do we have a chance to exploit it? So what is a measure to figure out how fast are we? For me, a good example is multigrid for Poisson. So they typically, a rule of thumb is a good multigrid needs, let's say, 1,000 flops per grid point. So it means a problem with 1 billion grid points, 10 power 9, and 1,000 flops per grid point means if you or if we would be able to exploit this full performance of 100 teraflop, we should be able to solve such 1 billion grid point Poisson problems in 0.01 seconds. Okay, let's assume we would be able to exploit only 1%. Let's assume we might have multigrid solvers with 1 teraflop speed, then still we could do it in 1 second, and that means the solution speed means how many millions degrees of freedom can you solve per second, and it means 1,000. So we solve a problem with 1 billion unknowns in 1 second if we would be able to exploit only 1% of such a 100 teraflop machine. So 1,000 million degrees of freedom per second is not so much, because it means I assume I can exploit only 1%. What is realistic? I guess you all know, if you check your sparse matrix vector multiplication, the main components in solvers, unless, okay, you will say, if you work matrix free, you will be faster. In some sense, I agree, but let's assume you do it not in a matrix free way, you do it with standard matrices. You see something like 100 till 300 gigaflop on the A100. If you do it with dense matrices, you immediately see 300 teraflop. So it's more than a factor of 1,000 faster. And in fact, when we analyze our multigrid solvers, and in fact, our most modern finite element software called feed-free with our geometric multigrid solvers, it's a little bit a shame for me, but I have to confess, typically, we are in a solution speed of 10 till 20 million degrees of freedom per second. So that means give me a problem on one node with 20 million degrees of freedom. Typically, I'm able to solve it in 1 second, but not much faster. So I'm typically, at least we in Dortmund, we are far away from this 1,000 million degrees of freedom per second. But that is not, it should not be surprising, because if you check this top 500, there's not only the LINPACK test, there's also this HPZG test. It's a kind of prototype multigrid or ZG, which includes many of the components of a multigrid code, sparse matrices, finite elements, and then it's clear. So it's already hard to reach 1 or let's say 4% of the available peak rate. So we are far away with this kind of technique from this exaflop rates and similar. It's more in the range of 1 petaflop and similar. Okay, so it means obviously with our standard sparse finite element multigrid codes, yeah, it's not so trivial to get a full performance. The other problem is this lower precision. So I think it's a trend due to AI. I don't know, it might be an interesting point for discussion. So I really fear a little bit that in a few years, most of our computing centers in Germany will say, dear scientists, be happy, we offer you very fast supercomputers with NVIDIA type, please use it. And I have to say, thanks, but I do not know what to do in lower precision. That means single or even half precision. So it doesn't fit into our finite element world for problems which are ill-conditioned and similar. And here you see the main problem. So typically, let's say Poisson, linear finite elements, you have a discretization error which behaves like h squared. So that is the blue line in some sense. If you increase the mesh size, the error is getting better. On the other hand, we have the computational error. So that means the round-off error. Or better, the round-off error is amplified by the condition number. And the condition number for Poisson goes like h minus 2. That's the red line. So that means if you calculate finer and finer, round of errors are amplified. And if you calculate where is the section of both, so when are discretization error and computational error approximately the same? So this is the machine tolerance to the power 1/4. So it means double precision with 10 to the power minus 16 means a mesh size smaller than 10 minus 4 will not help, because then you only see the computational error. Single precision with 8 digits means a mesh size of smaller than 10 minus 2 will not work, and half precision means you have 4 digits, so h is something like 1/10. I guess no one wants to use a supercomputer for a mesh size of 1/10. And it would be much better if we would find a way to reduce the condition number of our linear system. So if we could reduce it to a condition number O of 1, then this critical age would be only square root of tolerance, which would mean for single precision, we could easily handle problems of mesh size 10 minus 4, and even half precision might allow 10 minus 2, which already for many industrial applications might be okay. And what you see on the right is the result after prehandling. So the dashed green is a standard finite element, and you see level 5, so that means a mesh size of 2 to the power minus 5. Further grid refinement doesn't help, the error increases, while applying hierarchical finite elements, one of the candidates for prehandling, allows even in half precision with a much finer mesh size, and you also get much more accurate results. And with single precision, you're almost able to get the same results like in double precision. So what I want to show you in the following, what could we do to modify the linear systems that we are solving to, first of all, to take care that the condition number is smaller. Because if the condition number is smaller, then the round of error is getting diminished, and then there might be a chance even for our Poisson problems and similar to exploit lower precision. So just as a very preliminary summary in between, so I hope I convinced you a little bit. So first of all, parallelization in space will not be enough. So especially when you have problems with, let's say, million of time steps. So I think there one of the key tools are global in time approaches. And then I will show you a little bit what we do regarding parallel in time and simultaneous in time Krylov multigrid solvers. And accelerator hardware, I think that we all know standard sparse matrix vector applications or operations in double precision are slow on GPUs. Lower precision is not accurate enough, and it's also not clear. It's not only the question of lower precision. How do we exploit this tensor cores with finite element simulation? And I announce a little bit, I want to show you a little bit in the next minutes how we try to handle these problems. And the key, the buzzword is prehandling. The idea is, so you start with your sparse, ill-conditioned linear system, let's say a Poisson problem. And the first is what you apply is a prehandling. The prehandling just takes care that you solve the same problem, but the condition number is getting much smaller. Then we apply in 2D something which is called hierarchical finite elements. In 2 and 3D, we also talk about generating systems. I will shortly explain. And then based on this, we design special solvers, which are not only able to work fast in lower precision, but they are also, some of them are able to exploit tensor cores. So what's the idea? As I said, the idea of prehandling is, or you could also call it explicit preconditioning. So that means I make preconditioning, but I calculate explicitly the transformed matrix. So it means from ax to equal b, you switch to a tilde x tilde equal b tilde. So it's clear both should lead in exact arithmetic to the same solution, but the aim is that this new matrix condition a tilde has a much better condition number. And prehandling means, so the requirements, so when you apply prehandling, the new matrix should have a much smaller condition number. the new matrix should still be sparse, and the transformation should be fast, let's say something like n log n. And in fact, today we know about two successful candidates. The one is called hierarchical finite elements. So in that way, I have a luck. I'm quite old, so now I'm 61. And I remember techniques which had been developed in the 80s and 90s by especially people like Iser and Hunt, hierarchical finite elements, which is a very interesting technique. And what you see, the picture, the first picture in the top, you see the three basic functions for the mesh size 1/4, but with a hierarchical finite element approach. And there's something called generating systems. I think it mainly goes back to Michael Griebel in the 90s. And here you see the second picture. How do all finite element basic functions look like? And you see it's more than three, because you take into account not only the mesh, not only the basic function on the finest mesh, but also on the coarser meshes. So the idea is, you must say, hierarchical finite generating system. You just build up the system, which is very easy reproducible from standard finite element approach. And then, for instance, you just apply a conjugate gradient method on this new matrix. So first of all, the condition number is getting very small. And that's what you see here on the left side. When I solve it, even in single precision, in half precision, this is the green plot, allows me now to get an error of almost 10⁻⁴ in mesh size 1/512. And in single precision, now you are able to work with mesh size 1/4000. You bring it down to errors of 10⁻⁵ and smaller, and everything is done in single precision. So this is what prehandling is doing. The problem is only that helps us how we can solve problems in lower precision. It's not clear how to exploit tensor cores. And here the main idea is, and I've seen Dustin Ruder, at least at the beginning, was also in the auditorium. So with him together, I developed these techniques. And the main thing is we take a special numbering. So first of all, we have the unknowns on the skeletons. These are these gray lines. And you have this interior unknowns, the red unknowns. And then we make a special splitting, and most of the unknowns are this interior. This is the lower right block. So then we go to a Schur complement. We can either calculate it exactly or we do it iteratively. And that we can do again in lower precision, because this transformed matrix, after applying hierarchical finite elements or generating systems, it's much better conditioned. So it means even this low system, this system with the matrix A tilde, for this skeleton unknowns, this system is much smaller, it's well conditioned. And in between, you have to apply the C-1. So these are these local problems. And in fact, what we do is we really calculate this inverse. It's a small dense matrix. And sometimes, depending on the mesh structure, these are even always the same matrices. And that instead of doing a block diagonal system, you can also say, take always the same matrix, but with different right-hand sides. And that corresponds really to a dense times dense matrix. And there typically we are able to exploit the peak performance of NVIDIA and similar tools. So the storage, when we do this, what you see is we can really handle this. And at the end, we have a storage size of, let's say, for instance, 43 non-zero elements per unknown, which is quite good, because even a standard 3D bilinear finite elements tensor has something like a tensor width of 27 or 27 non-zero elements per unknowns per row. So that means the matrix is still sparse. We can exploit everything. It's fine. And how fast is it? So you've seen we make a splitting into skeleton nodes and interior nodes. If you make the interior nodes larger, then the problem is these dense matrix parts are getting bigger. So, but on the other hand, it's also getting faster, because there you can exploit the 100 teraflop. And there you see, for instance, we play around, we try to figure out what is the optimal coarse mesh size. But what is most important is at the end, the number on the very right-hand side, because that gives us the resulting solution speed. The solution speed expressed in how many million degrees of freedom can we solve per second. And then even in 3D, we are in the range of 400, 500. And compared to what we do with our standard multigrid solvers, which is 10 to 20, it's dramatically faster. This was on a A100. For instance, if you switch to a H100 Hopper, so this machine is 2-3 times faster, and you get it. So that means we really can scale this, but you also see is this H0. So that means to design the corresponding numerical algorithm is really extremely hardware oriented. And what we typically do is, if we get a new GPU, we make like basic tests. So what is the optimal coarse grid size and so on. And that determines us in a kind of hardware oriented style, what is for this machine the optimal configuration. So, and only finally, because this is very new, we do this as a multigrid. So what you see here is the generating system for a freeze-level approach. And what you really do is you write down the matrices for all levels. And now you apply to this system typically a conjugate gradient. And for those of you who are familiar with old techniques like BPX and similar, Brembel-Pashak-Xu, so for instance, take this matrix, apply conjugate gradient with Jacobi preconditioner is the same like BPX. Take this matrix, apply conjugate gradient, and take a symmetric Gauss-Seidel preconditioner is the same like a geometric V-cycle multigrid. And what we do at the moment, we apply to this system multigrid. So as I said, this system, this matrix E, is pre-handled and it has a much lower condition number. So it means we can do everything in lower precision. And that is what you see here. So the green, again, is half precision. And the dashed line is if you do standard finite elements, then level 4, it stops. And if you apply this technique with this generating system, even in half precision, we can get errors of 10⁻3. In single precision, there's no difference between single and double precision. And on the right-hand side, you see the corresponding multigrid size, depending on the coarse grid size and so on, V cycle, F cycles, different number of smoothing steps. So it's a very fast multigrid solvers. And as I said, the important thing is we do everything, every operation only in single or in half precision. And nevertheless, we get the same accuracy like in double precision. So that is the idea and the realization of this pre-handling. Okay, that will be one part in the Navier-Stokes solver I want to show you, and it will be important for all these pressure Poisson problems. But I just want to, if you give me a few minutes, I just want to show you a little bit how do we do this parallel in time simulations. So and the idea is for those of you who are experts for designing solvers for incompressible flow problems. So what you see here is typical way you write it down is a subtle point problem. And to do this for several time steps simultaneously, you just write down, but you just write it down for, let's say, for k time steps simultaneously. So then you have k velocities, k pressure, and you just write it as a huge system. And then you use the abbreviation by calling it A, B, B transpose. So that means on this level, you do not see a difference between a sequential, so I mean one time step scheme, and many time steps. So then how to solve it? One typical approach is the pressure-Schur complement approach. So that means you eliminate the velocity. You go to the pressure-Schur complement, B transposed A minus 1B. And then the only art is how do we construct preconditioners? The preconditioner C, which should be a preconditioner for the Schur complement. And the very interesting thing is there's no big difference between you do it for one time step or you do it for many time steps. There are two quite techniques which are quite popular. It's the PCD preconditioner, it's the LSC preconditioner, and both consist of many Poisson problems or mass matrix problems. And now what you will see is the preconditioner consists of solve convection diffusion problems, non-steady, and solve Poisson problems. So in fact, the final preconditioner for k time steps looks like that. You see a lower triangular structure. So it means applying the preconditioner means solve first of all for all u velocities. It's a non-stationary convection diffusion problem. I will show you how to do it with parallel in time multigrid. Then the same for the v velocity. Then you apply the divergence, and then you solve the pressure. The interesting thing is typically you solve one pressure problem, and here you have treated all velocities for all time steps before, and now you solve a pressure Poisson problems for all pressures for all k time steps independent of the velocity. So, and if the mesh does not change in time, it's always the same matrix C. And that again, you can say, instead of solving k problems with a matrix C, you solve one problem with matrix C and k right-hand sides. And it means we are exactly in the situation where we designed the prehandling, because we have no one Poisson problems, but with many right-hand sides, which immediately allows you blast-free techniques and all the things where we apply, or where we can apply these techniques I showed you before. Okay, there's only one thing. You might say, the problem is Navier-Stokes is not linear. It's a nonlinear problem. How to treat a nonlinearity? And in fact, what we do is we just make a global in time Newton. So that means we apply Newton to the Navier-Stokes equations to k time steps simultaneously. Because the idea is, if the Newton works fine, you have quadratic convergence, and quadratic convergence means as soon as you have gained one digit, then the next step is 2, 4, 8, and so on. And this is more or less independent of how many time steps you do. If you ever reach this range of quadratic convergence, it's extremely fast. So that's the idea of this global in time Newton. And what you see here as a first test case, this is this bench free for a higher Reynolds number for a Carreau type model. So that means non-Newtonian flow model, high viscosity, which is really corresponding to this polymer extrusion problems I've shown you before. And what you do here is you increase, you calculate from t equals 0 till 8. So the velocity is increasing, going down. What you see here is, for instance, also how the viscosity develops, the nonlinear, the shear rate. And this is a simulation with 3,200 time steps. And we solve this 3,200 time steps simultaneously. And here it takes 11 Newton steps. Per Newton steps, it required between 4 and 7 Ausen steps. And in each Ausen step, we have to apply convection diffusion and Poisson solvers of the previous type, which takes, let's say, between 4 and 10. And this has an enormous potential for exploiting the computational efficiency. The problem is, I think, for those of you who are familiar with parallel in time methods for convection-dominated problems, higher Reynolds number, the Newton has a problem, because it's also clear, as we know, if the start value for Newton is bad, you might even have divergence. And similar things are working here. In principle, you might work in a nested way, first work on a lower level. But what you see here, for instance, is the lift curve for this bench 2 test case. And level 3 and 4 are very similar. It's blue and green. But level 2 looks completely different. And if you take the level 2 solution as a start solution for level 3, the Newton has extreme problems. The surprising thing is, Pollock and found a way, and I could not believe, it's called Picard-Newton. So the trick is, instead of making Newton or Picard iteration, you just do one step Picard, one step Newton, one step Picard, one step Newton. I could not believe, I could not imagine, but that really helps, even with bad start values, to stabilize dramatically this complete Newton approach. And now we can even solve such long-term nonlinear problems with this help. And I could even imagine with some Anderson acceleration techniques, it will even improve. So that means the Newton, perhaps we have under control. So in each Newton step, you have to solve a non-stationary Ausen problem. The problem is, I've shown you this pressure-Schur complement technique, and the main ingredients are Poisson operators, mass matrices. Mass matrices is good for highly time-dependent. Poisson operator is, mass matrix is good for diffusion-dominated. Poisson operator is good for small time steps, but there was no preconditioner for the convection. And that is still a problem today, what are good preconditioner for convective pressure sure complement preconditioners, and that is what you see here. The Ausen solver of that type with these two preconditioners is very sensitive also with respect to the number of time steps you solve simultaneously. If it's getting more, so calculating always in the first row, you calculate for 2 seconds, so then it's fine. If you do the same for 4 seconds, you see the convergence behavior is getting much worse, and doing all time steps, that means calculating from 0 to 8, the Ausen solver is getting bad. And there are 3 techniques. The one is so-called augmented Lagrange. So that's a very funny trick. It's also known from sequential, but we do the same in time. And the idea is when you apply this augmented Lagrange, so you get a convergence behavior which is very good, and it does not need even multigrid. So it means what you see on the left side, depending on the augmented Lagrange stabilization parameter, it takes only, let's say, 5 GMRS steps, and we solve the corresponding Poisson problem. The background is you add a stabilization term which is consistent, because you see BMP minus 1 B transposed does not change the solution, not at all, but it changed the condition number, because the preconditioner is now not this Poisson operator Ci minus 1. It also contains this mass matrix minus 1 with this stabilization parameter gamma. And if you make gamma large enough, this mass matrix is getting dominant, and this preconditioner can be calculated exactly, and everything is perfect. And that means you do the same now on the time level. You calculate the preconditioners, and now the only thing what happens is your preconditioner is now essentially a pressure mass matrix. So, but you might expect nothing is for free. The problem is now you have to solve the corresponding velocity problems, and this stabilization leads to very ill-conditioned problems, because this is a singular matrix which you add. And the problem is standard multigrid doesn't work. You see here standard multigrid using Jacobi smoother, no chance at all, but also due to Wexum, he found a way, so some patchwise Jacobi solver, it works. So that means we are also able, even for large number of time steps, to solve the corresponding problems. So that means at the moment, we seem to be able to combine this augmented Lagrange to combine with parallel in time multigrid. It works fine. So even 1,000 time steps, it seems we can handle simultaneously. And the number of multigrid iterations is always something like 10 or a little bit more. And it doesn't matter whether you treat sequentially time step by time step or you solve 1,000 simultaneously. Another way is we also do this with simultaneous in time approaches, but this I skip a little bit because it might take too long. An alternative is, perhaps some of you know Wanker-like solvers. So in a way, you solve local problems. It's very popular for, let's say, Navier-Stokes problems, especially for larger time steps. It works fine. But finally, I want to say this, what at the moment is my biggest hope. So again, for those of you who are a little bit older, so perhaps some of you know discretely divergence-free finite elements. So it's a technique that you eliminate the pressure because the basic function are discretely divergence-free. The good thing is then the Navier-Stokes equation or Ausen equation or Stokes is not more a subtle point problem, it's a scalar problem. So you can apply all solvers what you want, ILU type and so on. And the problem is only the last work was more or less in 80 or 90 years. In fact, it was my PhD thesis in 1988. There I developed multigrid solvers for 2D divergent finite elements. But for 30 years, no one worked in the 3D realization because everybody was believing that cannot work. So for those of you who are a little bit more familiar with this, there's a problem with how to create the basic functions because you have more ansatz functions than basic functions. So it was completely unclear. The good news is, together with my collaborator, Christian Lohmer, he realized this last year, and it works. We have now, for the first time, a full 3D optimized divergence-free solver. So that means no more problems with solver because everything is scalar, it's regular, and that at the moment you see also we embedded into a parallel time approach. That is my hope for the next year, that we really might bring everything together, this parallel in time with this lower precision and so on. And that makes me optimistic. So I really see good chances based on this approach that we might get, some other accelerations. So almost 1 hour. Yes, to come back. So I would say, yes, there is a chance that we can use massively parallel and lower precision accelerator hardware. So even for flows of industrial relevance, I hope I could show you that what might be mechanisms how to do this. And I would say it seems to be possible. And seems to be possible means to me, if that works, what is potentially available, we should talk about CFD solvers, which are 1,000 times faster. And having a speed up of factor 1,000, then in the next step, I really would like to handle this error control, because I think that is the big difference to AI. We, with our very rigorous mathematical techniques, at least I see a chance that we make a simulation and at the end you make flow around the aircraft, let's say, and the result is that the code tells you, I guarantee you that the drag is accurate by at least by a maximum, the error is maximum 5%. Then you could accept it. It might say, oh, I can only guarantee by 20%. Then at least we know, or we have to decide, is 20% enough? If not, we refine. Or it says, I'm sorry, but I can guarantee only 200% error. Then at least I know I should not trust such a simulation because the error of 200% is meaningless. And this is what I believe must be one of the next steps in CFD simulations, that we really are able not only to produce qualitatively good results in a good manner, but really at the end, you get a guarantee that a certain accuracy is guaranteed. That, in my opinion, is one of the most important steps. Also, that really our mathematical techniques are accepted in the community. And I think it's also very important, again, in the interplay with AI, because AI will need very good trainings data. And I think it doesn't make sense to make training of AI if all the trainings data are completely garbage. So I think it is necessary. I believe it is possible. And I would say it must be possible, because if we do not solve this, then it really might happen, if you remember my first or second slide, that someone says, forget about this millions for mathematicians and so on. They try to do this in 30 years. They are too slow. There's a new generation of AI tools. They seem to be much better, much cheaper. And that is not what I want to see in the next years. And that is why I think we have to intensify our work, really, that we get it much better, much faster. And as I said, as a mathematician, I'm very optimistic we will be able to handle this. Thanks.
All right. Thank you so much, Stefan. No, it was great. Really interesting, stimulating, thought-provoking. Let's open it up for questions. If you have a question, either raise your hand or just unmute and feel free to ask. Hey, Dennis.
Hi, Dennis Uckermann from Ruhr-Uni Bochum here. First, thanks for the really great talk. Please.
My neighbor city, that's interesting. Yeah. So I have to talk with someone of Bochum, 10 kilometers far away, via Lawrence Livermore. That is really strange. Yeah.
So I have a question regarding, do you have performance numbers here? I mean, we know that the HP bug problems, they do not scale well on the large clusters. And here, sure, you now show a way with the Schur complement solvers how to utilize tensor cores, which is already a really great progress. But do you have numbers how much it actually increases performance of our solvers now? Or how much hardware utilization can we expect to get out here?
I have to confess, I can only say it for parts. So Sanyo also announced we have here, so Mitya Kusmin and me, we have a quite large group in Dortmund, so many people are working on these topics, but even this huge group at the moment was not enough that we really realized full tools. So I can only, at the moment, I can show you also real performance results regarding this pre-handled Poisson solvers. I can show you results. How do these Schur complement solvers behave? But also, what about what happens if you take more processors? So, for instance, this time simultaneous or time parallel approach, it takes at least 3 or 5 times more effort. So that means you need at least 10 times more nodes or whatever to get some speed up. So for the subtask, I can show you results, but at the moment, we do not have finished so far a complete solver. And then I fully agree, will be interesting how much will be the speed up compared to the standard solvers. And still not finished, only for subtasks.
Sure, thanks. I'm really looking forward for results.
Yeah, it's also clear at the end it will be much less than we might predict from the theory, because we all know if you have 100 components and there must be only one of them which is not optimal, it will bring you down with everything. So I guess at the end it will be huge work to optimize everything and that everything works together in a perfect way. But at the moment, I hope I could show you a little bit. So these are some components which at least might be candidates for such work. Because, for instance, this prehandling, this is really, I'm very sure most of you are not familiar of this prehandling, because it's really a quite new idea. We try to publish it, to spread it, but so these are all components which really in a hardware-oriented way have to design and then at the end to adapt it to perfectly fit together.
Right, great. Thanks, Dennis. Other questions? So all this idea is very interesting. Prehandling, explicit preconditioning, I can see that being beneficial. Also, this Schur complement for tensor cores. Let me ask about that. This Schur complement approach, does it work on structured grids with maybe adaptive mesh refinement? What you showed was kind of structured.
Right. You talk about the Schur complement when I talked about this Poisson solvers in context of prehandling.
Yeah.
It works also. Let's say what you need is in fact a multigrid hierarchy. So it does not work. So for me, it's like, let's say, there are two, I don't want to say religion, but there are two worlds. There's the algebraic multigrid world and there's the geometric multigrid world. I'm geometric multigrid world. So for me means it doesn't help me to get the metrics. I have to handle everything simultaneously, the grid generation, the assembly, and the solver. And it means this is really based on the idea you have a hierarchy of levels and that is exploited. So I must be master on this. On the other hand, it also works if your coarse mesh, for instance, is unstructured and then during refinement, each element is refined in a structured way. That kind of meshes work fine. But if you would give me an arbitrary mesh, so at the moment I do not know, can we transfer it to algebraic multigrid approaches?
Right,
so it's much more restricted to that you are mastering the grid hierarchies. Okay,
so what's happening really is you take a coarse mesh from the multigrid hierarchy and you just eliminate the interior degrees of freedom on that coarse element, define interior degrees of freedom. Is that
exactly? In some sense, it was also, I think there are other names, but you eliminate the inner nodes, then you only work on the skeleton.
Yeah.
And for the inner nodes, these are the mass of the grid points. These, on the other hand, you try to exploit. So it takes more operations, but there's a chance that you do it with more dense operations.
Understood. Right. Other questions? Hey, let me ask another one.
For sure.
The parallel time, also something we've been interested in. You probably know about the X-Grade project here in Livermore.
Yes.
MGrid. In this, one interesting thing that also always comes up in this setup, can you do adaptive time stepping?
Yes. So for instance, at the moment, so this to have adaptive time step is not a big problem. So what at the moment would be more problem if you change the space mesh in each time step, because at the moment I really exploit, and that is for me a very funny thing. So also from more or less from a philosophical point of view. So we know from, let's say, Poisson, Navier-Stokes solvers, there's this good old Chorin or Van Kant splitting. So given a pressure, predict the velocity. Having the velocity, put it to the right-hand side, solve the Poisson problem. And what is for me absolutely amazing, you do this for, let's say, 1,000 time steps. So given the pressure for all 1,000 time steps, you solve for the velocity, which is now a convection diffusion reaction problem. And now you calculate all velocities, let's say with parareal, which also belongs to this class. And then you solve the Poisson problem, and now you solve the pressure for 1,000 time steps simultaneously. And that really works. And that, I must say, I could not imagine. And so that means then really, if you have fast Poisson solvers, that's a perfect situation, especially, as I said, when the mesh does not change. You have always the same Poisson operator, but let's say with 1,000 right-hand sides. And there you have such good chances to exploit a dense right-hand side and things. So this really, I must say, surprised me. And okay, it helped me a little bit, since when I started, my habilitation was also on pressure Schur complement solvers in a sequential way. And the good thing was I could transfer it to this many time step cases. But it's still...
Yeah, sure, go ahead.
Yeah, it's still also open problem. That's the same as in the sequential way. We still do not know what is a good preconditioner if it's convection dominated. There are these techniques, PSC, LSC, commutating preconditioners, and so on, but nothing works perfect. And the problem is you see the same here if you do it with, and that is why I hope if that works with this discretely divergence-free finite elements, really works, because then you get rid of all these pressure Schur complements and sample point problems, and you just apply GMRES with ELU, with drop technique, you have a good smoother. That is my dream.
Okay, but just to follow up on something you said earlier, if you have, for example, adaptive mesh refinement, that will be challenging in this parallel time, where the mesh will change and the degrees of freedom will change from time step to time step. That will be challenging.
But again, also I think that is, like we always said, it's also, let's say, a question of perhaps also hardware-oriented philosophy, numeric philosophy. So in former times, when we were estimating when is a numerical algorithm better than the other, we were counting how many operations. And it's clear n squared of algorithm is worse than n. But today, so we have operations which might act in the 100 teraflop regime, and others are working with 20 gigaflop. So I think this is also very interesting. And regarding adaptivity, the question is, would it be possible to work with 100 times more unknowns if you can exploit GPUs, you get the full performance, because then even if it takes 100 times more work, at the end you might be faster. And I think that is also an interesting question. How do we design adaptivity strategies which also exploit these special features of today hardware?
Very much agree. Okay, other questions? Anybody else? This is your chance. Have Stefan coming all the way from Europe to us.
So one point will be interesting, because I think also there we could work together. So let's say at the moment there's this one word geometric versus algebraic multigrid. But there's also the other, I don't want to call it fight, but matrix-free versus matrix-based. And the thing is, what might be interesting, so that I would also like to discuss with you. At the moment, it seems for us, we really first of all have to calculate the complete matrix in double precision. Then we apply this prehandling, and then we restore the resulting matrix in single precision. So far, we were not successful to simulate this approach in a matrix-free way. So because it seems at least we are not the experts, but so far we were calculating global matrix, do all this pre-handling, and then with the final matrix, then we could do that. I would, if we meet next time or like that, it might be really interesting to combine, because I see the advantages of matrix-free.
Yeah.
And now the question is, could we combine this matrix-free advantages? On the other hand, what we do, that we really can exploit lower precision, even half precision, without losing too much accuracy. And I also think there must be a way that we can combine both worlds.
Yeah, so for us, particularly for higher order discretizations, matrix-free is very appealing. It's because of something you said earlier. The flops don't matter as much anymore. It's really the memory access.
Yes.
And if you're a high order, you cannot assemble a matrix. It's just too expensive to read it from memory.
Yeah.
So matrix-free there makes a lot of sense, but we still assemble kind of preconditioning a matrix just for preconditioning that is sparse, that is cheap to read from memory, but is somehow a spatial equivalent in some cases. We call this low order refined. There you can use prehandling, lower precision, all of that. So there is a natural kind of connection. I agree. It will be cool to connect the two.
Because I think, in some sense, what you work in a kind way of mixed precision, for instance, you might do but what I avoid this, because I can do everything in lower precision. So, which on the other hand really speeds up. And as I said, I fear a little bit. So when I see what NVIDIA is doing, I really fear that I don't know what's coming beyond Blackwell, but I have the feeling they reduce double precision even more and more. And this funny, I don't know, does you or does someone here from the people have experience with this Trainium 2? So did ever someone solve Poisson problems or finite element problems on this Amazon device? So which, as I've shown, so we talk about a device which in single precision has several hundreds of teraflop, but they do not even say anything about double. So I have no idea. And that is what I fear a little bit. What will we do in future if, you in the United States are a little bit used that from day to day, situation might change disruptively. And what will happen in this hardware market if really people say, come on, this double precision, it's nothing worth, and we only concentrate on single precision. And I think there we really have to work together, on one hand making pressure that double precision is still necessary, but on the other hand also to be able to exploit this lower precision stuff.
Yeah, I think we have very similar fears and concerns, and we are trying to push back. This market is very driven by AI these days and what they need. I don't have experience with that chip. We have a lot of experience with AMD and with El Capitan, and with NVIDIA.
So that would be very interesting also. At the moment, we really try to get access to this AMD, so which seems to be not so easy in Germany. So it's easy for us to buy NVIDIAs, but to buy AMD, it's much harder. So I don't know. So really, I have no experience, but it's clear if I see these are the number 1 or number 2 machines in the world, and also their single precision power is also quite impressive. So
yes, yeah, they're very. I mean, just kind of general statement. They're very similar to NVIDIA in many ways. It's the big difference is that maybe in the software ecosystem and the price.
Yes.
And I think a lot of these new chips went straight to El Capitan. That machine just got accepted recently, so they'll show up on the market maybe a little bit later.
Yeah.
Okay. Anybody else has comments, questions? Some controversial topics here, so I'm sure people have opinions. Wesley has a question.
Yeah,
Go
so
for it.
You mentioned the importance of providing the, how big the error is. Is it 20%? Is it 5%? So what is the path forward for that? Especially for like ill-conditioned problems, I guess, when we have turbulence, maybe. But even for simpler problems, what techniques do you think important for that? Oh, okay. Let me repeat. With regard to your comment at the end about providing relative error for the solutions that we compute, right?
Okay, yeah.
If it's 5% or 20%. So what kind of techniques do you see as a good candidate for providing this?
Okay, so that's very easy for me because my doctor father was Ranacher. And so when I left Heidelberg at the time, so he was getting more and more busy with this a posteriori dual-weighted error control for user-specific quantities. So it means you have to solve dual problems, which is quite hard because for a non-stationary Navier-Stokes equation, you have to solve a linearized Navier-Stokes equation backwards in time. So, and you have to do this several times and so on. That's why I say it might cost 10 or even 100 times more. But at the end, if you do it in a good way, and I'm not the expert, but from a theoretical point of view, you might have control even over the constants. And so this is my vision, because I think all of us, we are proud on our simulations. But if someone would ask us, so would you give your small finger to guarantee that the simulation satisfies, so like, let's say in civil engineering, the bridge will not break. So typically that we do not do. And I would not do with this because in 99.9% of my simulations, I trust my simulations because I did so many. But there is nothing which is mathematically founded. And if you see, for instance, I know it, this technique, what I mentioned, is based on finite elements. I guess you can do the same in time, or you can do it with discontinuous Galerkin and higher order. You might do it also with different techniques. But I think that's also, I think we in the community, perhaps we should check again more carefully which of these techniques have a potential. And then also we should try to get some fundings and so on to convince the people, because I think that's really important, because AI will never be able to do that. They can only be, in my opinion, as good as the training data. But if there is a special flooding which never happened before, they cannot predict. We could predict with our mathematical tools. And I think this is our big potential, but it is also extremely hard. And to get a generation of PhD students and postdocs to do this might require several years, but, and I'm not the expert for this, so there perhaps you have to bring together the HPC experts like we here together with this error control experts, very deep mathematics, but yes. So if you check papers by Rolf Ranacher, so he's doing error control.
Okay. So what about, well, okay, that's I think, sufficient. I don't want to prolong the discussion. There are, I guess, potential different approaches with.
Yeah, there are many. So the thing is, only as I'm not the expert, I only know about this approach because I'm a finite element guy. So my education was in finite elements. At least this technique I understand. There are many others, but I also have to confess I'm not so deeply involved to give some. Yeah, I should not say about much. Okay.
Thank you.
Okay.